A toroid is essentially a solenoid bent into a circular shape. It consists of a hollow circular ring with many turns of insulated wire wrapped around it, characterized by its inner radius A and outer radius B. Now consider the region outside the entire toroid. Any loop here encloses both the inward and outward currents of equal magnitude. These cancel each other out, resulting in a net enclosed current of 0 and a magnetic field of 0. The magnetic field is only non-zero within the core of the windings. Here, a circular loop of radius R encloses 10 turns of wire, each carrying currents I, making the total enclosed current then times Y. Due to the circular symmetry of the toroid, the magnetic field B is constant in magnitude along our circular path. The line integral of dl around the circle simply becomes the circumference, 2 pi r. By equating the two sides of Ampere's law, we find that the magnetic field B equals mu0 times n times y, divided by 2 pi r. This shows the field strength depends on the position r within the core. Unlike an ideal long solenoid, the magnetic field in a toroid is not perfectly uniform. It is stronger near the inner radius and weakens slightly toward the outer radius, following a 1/r relationship. For a toroid with a very small cross-section relative to its radius, we can use the average radius to define n as the number of turns per unit length, simplifying the field expression to mu0 n I. In summary, the magnetic field of a toroid is completely confined within its core. It is 0 both in the central hole and in the space surrounding the exterior of the device. Toroids are essential in technology, used in transformers to prevent flux leakage and in fusion reactors like tokamaks to confine plasma. This concludes our study on toroidal magnetic fields. Generated by Vision Solve AI.